Welcome back to Honors Calculus. In this video, we're going to continue our discussion on extrema with the idea of the first derivative test. The first derivative test is going to supplement the idea of relative extrema that we talked about in a previous video. We've seen that given a continuous function, we can identify that critical points occur where the function's derivative is either 0 or undefined. And we know that every relative extrema occurs at a critical point, although not every critical point represents a relative extreme value. The first derivative test bridges that gap and will allow us to identify which critical points are relative extrema and which ones are not. So let me get my head out of the way and let's jump in. We're going to start with the relatively simple idea. That's not a pen, that's a pen. We say that a function f is increasing on an open interval from a to b if for all x and y in ab with x less than y, f of x is less than f of y. So if you take any 2 points in the interval and order them and evaluate the function at the smaller point, you get a smaller value than when you evaluate the function at the larger point. We say that f is decreasing if and only if for all x and y in AB with x less than y, f of x is greater than f of y. Once again, one of those things where it's so similar, I'm just going to take the copy and paste route. So instead of increasing, we are going to talk about decreasing. And instead of f of x being less than f of y, this is where f of x is greater than f of y. An increasing function has a graph that looks something like that. A decreasing function has a graph that looks something like that. Very tricky ideas, things you should be familiar with from previous mathematics coursework. In this course, our goal is to, again, use that and put it on a more firm theoretical footing. Forgot a word in there, sorry about that. Let's let f be a function differentiable at some point c. We will say that f is increasing at c if and only if f prime of c is greater than 0, and we'll say that f is decreasing at c if and only if f prime of c is less than 0. Right, so using the derivative to take this average rate of change and turn it into an instantaneous rate of change, and then using differentiability and why am I getting ahead of myself in this video? Sorry about that. Now I have the whole statement correct. Let's let f be continuous on a closed interval from a to b and be differentiable on an open interval from a to b. And we will say that f is increasing on AB if and only if f prime of c is greater than 0 for all c in AB. All right, so this theorem is giving us a new way of looking at the general idea that we had before. And to prove this theorem, we will employ the mean value theorem. This is an if and only if statement. And in fact, one direction is fairly straightforward. If we have that the function is increasing, then it's fairly easy to say that f prime of c is greater than 0 throughout the interval. But if we have that f prime of c is greater than 0, it's not obvious that the function is always increasing. So let's tackle that by taking an interval, open interval from a to b, so that f of x is greater than 0 for all. Oh, me and details today. I apologize. Let's try to stay consistent with things. F prime of c is greater than 0 for all c in a, b. And let's pick x and y in AB such that x is less than y. And I want to make a note that f is continuous on the closed interval from x to y and differentiable on the open interval from x to y. The reason for that is very simply, xy is a subset of AB, and our theorem stated that f was continuous on AB and differentiable on the open interval AB. So because we have that, we can be assured here that when we take a smaller interval, we also have the same result. Right, but by the mean value theorem, there is some point c in xy such that f prime of c is equal to f of, we set that up as f of y minus f of x all over y minus x. And by our assumption, f prime of c is always greater than 0. So this is always greater than 0. And since I picked that x is less than y, that means that y minus x is positive. And if I multiply both sides of the equation by y minus x, I get f of y minus f of x is positive. So let me go off to the side and put the note in. We know that x is less than y, and I used that to say that y minus x is positive. So we can multiply by y minus x on both sides, giving us that f of y minus f of x is positive, which means that f of x is less than f of y. And that's exactly what it meant for a function to be increasing. So only a proof of half of the theorem. The other half is, like I said, comes back to if the function is increasing, then f prime is positive, is kind of our earlier statement. And we could prove the same thing for decreasing. We won't write it out, but we could say that f is decreasing on AB if and only if f prime of C is less than 0 for every C in AB, and the proof looks almost identical to the one we just went through. So I'm not going to do it again. But with those ideas in our back pocket, we can then develop the first derivative test. All right, let's let f be a real valued function of one real variable, which once again is continuous on a closed interval from A to B, and once again is differentiable on the open interval from A to B. And let's take a point C in that interval, where C is a critical point of F. I should state this the other way. Words and I are not getting along today. If F is increasing on the interval from A to C and decreasing on C to B, then F is a relative has. F has a relative maximum at C. And vice versa. If F is decreasing on AC and increasing on CB, then F has a relative minimum at C. I don't feel that we need to prove this. This is kind of how I took the definition of relative extrema earlier in this lesson. So instead, let's just use this and dive in and see what we can do with it. So let's consider the function, sorry about that. Let's consider the function f of x equals x to the fourth plus 1 over x squared. And our goal is to identify any relative extrema. First thing I want to notice is that this function is undefined when x is equal to 0. Our first derivative test only works where a function is continuous on a closed interval and differentiable at an open interval. When we have a discontinuity, the first derivative test doesn't work near that point, and so we have to be careful. So I'm going to make note of the fact that f of x is undefined at x equals 0. And we will just test around that. You'll see what I mean as we get into things. But the first derivative test asks us to look for critical values. So I'm going to take the derivative of this function. Using the quotient rule, we're going to have the derivative of the numerator, which will be (4x cubed) times the denominator, which is x squared, minus the numerator, x to the fourth plus 1, times the derivative of the denominator, which is 2x, all over the denominator squared. And simplifying that a little bit, 4x cubed times x squared is 4x to the fifth. Distributing, x to the fourth times 2x is 2x to the fifth minus 2x all over x to the fourth. Combining like terms, 4x to the fifth minus 2x to the fifth is 2x to the fifth. And let's cancel out one factor of x. So this is going to be 2x to the fourth minus 2 all over x cubed. A critical point is a point where this is 0 or undefined. We know that f prime of x is undefined when x is 0. Again, denominator, all the problems. But if I want f prime of x equal to 0, that means that the numerator, 2x to the fourth minus 2, is equal to 0. Divide by 2, that gives me that x to the fourth minus 1 is equal to 0. That factors into x squared plus 1 times x squared minus 1. X squared plus 1 is never 0 for a real x. It is 0 for some complex x's, but when x is I or negative I, that would be 0, but there's no real solutions. but x squared minus 1 does have some real solutions because that factors to x plus 1 times x minus 1, which gives us that x is negative 1 or x is 1. All right. Now, scrolling back up for just a moment, our derivative, 2x to the fourth minus 2 all over x cubed. And our critical points and our place where it was undefined, which happened to also be a critical point, are at 0, negative 1, and positive 1. Those are the places of interest. And our question is, in the space between, is the function increasing, decreasing, or 0? So we choose something over here, like say negative 2. We'll choose something in here, like negative 1/2. Positive 1/2 and positive 2 seems like great places to choose. And I want to evaluate the derivative at each of those points to determine where it's positive and where it's negative. F prime of, I should start at negative 2, is going to be 2 times negative 2 to the fourth minus 2 all over negative 2 cubed. Negative 2 to the fourth is 16, times 2 is 32, minus 2 is 30. Negative 2 cubed is negative 8. And we could reduce the fraction, but the only thing that really matters is that this is less than 0. So in this range over here, f prime is negative. Again, f prime can only change from negative to positive at critical values. That was the whole idea of critical values. So then we also want to evaluate f prime at negative 1/2, which will be 2 times negative 1/2 to the fourth minus 2 all over negative 1/2 to the fourth power. Right. Negative 1/2 to the fourth is positive 1 over 16. Multiply that times 2 and you get positive 1/8. 1/8 minus 2 is negative 15/8. And negative 1/2 to the fourth, no, that shouldn't be to the fourth, that should be cubed. Negative 1/2 cubed is going to be negative 1/8. Right. All told, that's actually just 15. But the important thing is that that's greater than 0. So between negative 1 and 0, f prime is positive. You'll find that between 0 and 1, when you evaluate at positive 1/2, you'll get that the function is negative. And if you try evaluating at positive 2, you'll get that the function is positive. I'm not going to go through those calculations. I invite you to do so on your own. All right. So before x equals negative 1, our function is decreasing in some way, shape, or form. After negative 1, the function is increasing. The function is undefined at 0. And then decreasing between 0 and 1, and then increasing after 1. What it looks like, I don't know. It's probably not straight lines, but straight lines get the picture across. Because by looking at the straight lines, we can see that at negative 1, we have some sort of a minimum, and at positive 1, we also have some sort of a minimum. So f of x here has two relative extrema. right? F has no relative maxima, but it does have two relative minima. They occur at x equals 1 and at x equals -1. So with that in mind, I would like you to take a look at the function g of x is x cubed minus 5x squared plus 6x minus 7. And use the first derivative test to identify any and all relative extrema. Take a few minutes to play around with that function, see what you come up with, and I'll see you in the next video.